All right, so for the bending moment, we will do the very same thing. In fact, I actually just copied the entire pictures from above and I bring them in here. And now to make our life easier, I will just erase these shear forces here and I will replace them with the internal moment, because now we worry about the moment. So I have this as a moment and I have this as a moment, and our goal is to express m of x and m of x. And of course, you can probably do that already yourself based on what I showed you above, but let me develop it for you anyways. So I now will take the sum of the moments, of course, about location x, right, about this point. And the way I will do that is by taking the sum of the moments about point x being equal to 0, counterclockwise positive. But let me clarify that this x here is the point x, so it's at a distance x from 0 here really. It, of course, still really turns about the z-axis, right? We explained this in some previous lectures. You understand that a 2D moment really doesn't exist. A moment always rotates about an axis. So now I can, however, develop my function and I can say that 0 is equal to, I start with my unknown, which turns counterclockwise. So positive defined m of x, if you will. And now I have to consider my ray. So I have ray, and this now has a lever arm, which is multiplied by x, and that is still in meters. And that now rotates clockwise, therefore the whole thing should be negative. So all this is negative, and by the way, this here is in kilonewton, let's say, or I guess we used newtons before, right? So let me put that in newtons. And now we have the ray taken care of. I need to now worry about my w, and that would be w1, which is the height of that rectangle, multiplied by a length of x. But before I do that, let me say that this is in Newton per meter, for example. Now I need to multiply that by a distance of x meters, which is really the resultant, right? You have seen that before above, but let me just clarify this because we need another term here. So this is f resultant. And therefore, I need to now multiply it by a lever arm. And this is where sometimes the confusion comes in. Well, what is the lever arm now? Because I cut somewhere through this force and it's always dependent on x. But it's actually not as difficult as you would think, because x is just the entire length of the rectangle. And we know that if we cut a rectangle at any point we want to, we always have the resultant acting at the center. And so the resultant really is at x half. So I now need to multiply this by x over 2, and that is also in meters. And please keep in mind that this is the lever. The last thing that I need to do is assign a rotational sense to this, because I'm rotating about this point. W1 is going down, therefore it turns counterclockwise, which makes it positive according to our definition. Take a look, please, at the units. They all match because we're looking at the moment here, and I have Newton times meter, or force times distance. And here I have a Newton per meter times meter, which is a force, and then times meter or distance, which then turns it also into Newton meter or force distance, which is what I need for my moment equation. And now you can see that we are dealing with an x and an x. So x times x is x squared, which makes it a quadratic equation. And again, you have seen this before, but now you know where it's exactly coming from. So we know that this x turns the moment function quadratic because we have the effect of the variable distance twice in this equation. And now I can collect my terms and write out that my moment of x is equal to positive ray times x minus w1 divided by 2 x squared. And of course, the whole thing needs a unit, which in this case is force times distance, or Newton meter. But ultimately, it's always a force times a distance because we're dealing with a moment. This now is a result, and it's something I will double underline. And I say that again, you will see an x square always for an evenly distributed force because you have a double effect in the x here in this equation. So I believe that concludes our moment function for an evenly distributed case in terms of x. So let's move on to the moment function for a triangular distributed force. You of course already know what's coming now and you probably can solve it yourself, but let's go through it together anyways. I start just like before with the sum of the moments about point x but about the z-axis, counterclockwise positive, and I set that equal to 0 so that I can now include all my terms. I start with 0 is equal to my unknown plus positive defined m about x. And of course, once again, I have to include my ray, so ray multiplied by x in meters, and ray we think in kilonewton here in this case. And the rotational sense for this expression is clockwise in this case because we're rotating about this point. It turns clockwise. Therefore, this would be negative. Same logic as above. And now I need to include my triangle, which again, the resultant force is base times height. So let's start with that. So the base, like before, is x in meters. My height was really equal to 2x in kilonewton per meter. And now I have a resultant force if I multiply this by 1/2, if I'm not mistaken. So 1/2, this really is the entire resultant force. So this is F resultant of the triangle that has a length of x. So now the question is, what is the lever arm of this triangle? And of course, you know that the lever arm for a triangle is always at the 2/3 or 1/3 side, and 1/3 from the heavier side. And this is really where we're taking the sum of the moments about. So I really need to look at x divided by 3, if you will, here. Because let's actually draw the resultant force in here for visual representation. I'm going to put it right here. So this is my F resultant, and that is what I calculated with x times 2x divided by 2. And now I need a lever arm, and that lever arm really is the distance that I will give you down here, where this distance now is equal to 1/3 x. And so I now multiply this by x divided by 3, and that of course is also in meters in this case, and this is the lever, so lever. And now I need to assign a rotational sense because this triangle rotates about this point as well. It turns counterclockwise, therefore the whole triangle is actually positive. No surprise there. But once again, you see that now I'm dealing with x times x times x. And so therefore I have a cubic equation for a sloped line when I deal with the moment function. Something you have used before and accepted before, but now you know where it's coming from. Let's recollect all our terms or rewrite it. And let's say that m of x for this scenario here is equal to positive ray times x minus, and I have the 2 that cancels out, so it's really 1/3 minus 1/3 x cubed. And the whole thing is also in force times distance units, but here I used kilonewton meter. So I'm just going to stick with that. And that is my result, which I, as always, double underline. And that therefore completes our moment calculation for a non-evenly distributed force, actually for a sloped distributed force or a triangular distributed force. So let's look at the entire page all together. We developed the shear function and the moment function for a evenly distributed load and for a triangular distributed load, and we clearly saw that we can replace what we have done with finite numbers in the beginning with an x, and that x then is reflected in our equilibrium equation. So for example, here in the shear force equation or the vertical equilibrium equation, and down here in the moment equation. And what we have seen is that the x really has a linear impact in this function here, as I explained to you throughout the section up here. And here x had a quadratic impact. And then, of course, you knew this before, that when you go from the shear force to the moment, that you really bring up your function by another x. But I have now shown to you why that really is the case. So this is something that often causes headache to students in the classroom. So please go ahead and study these equations particularly. I hope I did a good job on explaining that, but please make sure that you really understand where the x square comes from and where the x cube comes from here in this case, right? And I say it again, x times x is the height and the base of the triangle, and then we have the lever arm, which also needs to be expressed in terms of x. But I believe that is all available now on this page, and you are now ready to apply this throughout other examples. Let me give you one word of caution before we move on and before I show you some example problems. Of course, this is always only true for a specific domain. How do you define a domain? Well, in the past, we have done it by the significant values, because a significant value always occurred where something changed along x. So you can see here there's no change in the load case from here to here. And I don't know what happens here on the right. So for this case here, we developed the function really from here to here. This function, the shear force, and the moment function is really true for x equals to 0 to wherever this point here is. And then after that, something else happens, and I would have to develop a new function. But you have now all the tools to do that, and in the homework you will be challenged to do this for, I think, up to 3 or 4 domains. So beams have to be broken down in domains first, and then you develop the functions. But I will show this to you now as an example on the following pages. And so let's move on.